Although this screencast is going to walk us through some of the key terminology and concepts associated with Chapter 11 in our book, which Chapter 11 really is an extension of Chapter 10 also. The two of them go hand in hand. Last week we took a look at the idea of what hypothesis testing is at its core and what a null hypothesis is versus an alternative hypothesis and the idea of what level of significance is. And this week we're going to take that a step further, introduce some more language and terminology associated with these tests, and also conceptually what's going on. So at the core, basically, it's this. Imagine that you have a population of whatever phenomenon you're dealing with, and that population is normally distributed. And we have a sampling distribution here, which is a distribution of all of the possible sample means, centered at a mean and symmetrical on both sides. So this black colored normal curve is our hypothesized distribution. It might be, for example, information that we have from past years. We might have 10 years of data that gives us some information that we have to go on. And suppose then we have some type of new treatment that we're doing, some type of new either experiment, some type of new whatever it may be that you're conducting at work. And you want to test to see is this new product or is this new style of doing something significantly better or worse, or just in general, is it significantly different than what we've been doing as far as the data is concerned. So the hypothesized distribution is the information that you're going to compare to. It's going to be your basically your foundational set of data that you have from previous experience, and we're going to conduct some type of random sample of a new population, for example, and that population might be of students that are, going through some new process this year, and you want to see if there's a significant difference. So the null hypothesis is basically saying that whatever is the previous known information, we're going to say that's still true. That's our hypothesized, our null hypothesis. The alternative hypothesis is whatever we're actually testing for. The textbook uses many examples of, like, for example, SAT scores. And last week we were talking about the idea of SAT scores, and the mean SAT scores of the nation is 500. The mean is 500, and we're conducting a study of students here in New Jersey, and we want to see if the population of students in New Jersey is significantly different than that of the rest of the nation. And we take a sample of students, but before we even do that, and to walk through it here again, we are going to establish our null hypothesis and our alternative hypothesis before we actually even take a sample and look at any information. So let's walk through that right now. Say, for example, and this, to use the one we used last week, that we have an idea that the mean of the SAT scores is 500. And we're going to take a look at to see if students in New Jersey are significantly different than that. If they're significantly different than that, then we're leaving with that terminology, we're leaving ourselves open to the idea that to be significantly different, you may be significantly higher or significantly lower. So in that case, then our alternative hypothesis, which again tends to be whatever the actual purpose of our study is going to be the complement of this. If the null hypothesis is that the mean is equal to 500, then alternative is going to be that it's not equal to 500. And if that's the case, then we have what is called a two-tailed test. Circle this right here. Now on a two-tailed test, that means that we are going to take a look at the normal curve that we have for the population of students of SAT scores. And we're going to set up parameters on both tails to say that, all right, we understand that there's going to be differences, but we think that if we take a random sample of, say, for example, 36 students, and the mean of those 36 students ends up being beyond our certain marker here, I understand that there's a small chance that I happen to get a sample that happens to be low from a population that has a sample of, or a mean of 500. But I actually think it's more likely that this sample is from a population that has a score that's significantly different. So say, for example, going off to the idea of the hypothesized distribution here, I'm going to say this is all USA. All right, we're comparing all the students' means for the SAT scores. It might be that New Jersey, for example, if I took a sample, it might be that New Jersey actually has a population that's significantly less or significantly greater. And if that's the case, then we want to say that then, to back it up a little bit, we're again comparing to the original mean. If we end up with a score significantly lower down here, then we have two decisions to make. We can either say that, well, there's a slim chance that I actually get a sample that it's this low, but New Jersey happens to still also have a mean of 500. Or maybe it's more likely that the population in New Jersey has a curve that's less or lower. And we ended up getting a sample of students from that population. A two-tailed test allows you to have the possibility of scoring either significantly lower or significantly higher than what our hypothesized mean is. A one-tailed test is if our study, for example, is only worried about one side of that. If you actually can make a change at work, for example, you're usually making that change with the hopes of making something better. So let's just say that we think that the state of New Jersey did some changes to their education program, and we're working to increase our students' SAT scores. So in red down here, I have what would be an example of a one-tailed test's hypothesis statements. And in this case, we're going to say that our hypothesis or our study is that we think that the students in New Jersey have a mean greater than 500. That's our alternative hypothesis. That means then the complement of this, or the opposite of this, is that then our null hypothesis is that the mean is less than or equal to 500. So if it's a one-tailed test, then that's how that looks. A one-tailed test is going to have either greater than or less than for all the alternative hypothesis. A two-tailed test is going to have not equal to. Again, just like we did up here, not equal to 500 is the two-tailed test. If it's a two-tailed test, then we're leaving ourselves open to the idea of if we have data that puts it this far into one tail or the other, then we're going to say that it's actually more likely that our new sample is from a population that has a significantly different mean than our original hypothesized mean. If, for example, though, we have a one-tailed test, and in this case here I use the example of the SAT scores in New Jersey, and we hypothesize that the students in New Jersey score significantly greater, then we're putting all of our eggs in one basket, or we're taking a look at only one side. All right, now, how does this work? Let's take a look at the idea of, and we'll go with the whole idea of the SAT scores again. If the United States mean SAT scores is 500, and we want to take a look at New Jersey after some type of new change in the school system, and we want to see that are the students in New Jersey scoring significantly greater, then we would conduct a one-tailed test. We would put all of our level of significance, or the alpha, into one tail, and then we're going to compare. We're going to then take a sample. We're going to find a mean. We're going to go through the process we did the end of last week with the assignment, and we're going to find out where does that data that we got fall on this original normal curve. And if it falls into this tail area here, then we're going to say that the statistics show us that there is a statistically significant difference. And we actually think that New Jersey has a mean that is greater than 500. Now, a couple problems with this to realize now. In statistics, the whole idea of statistics is basically that we're taking educated guesses. And most of the time, when we're taking a sample of a population, it's because we don't have the ability to find the mean, or whatever the data is, of the entire population. And in fact, you may never be able to do that. So we're going to make judgments or decisions based on a sample. And if that's the case, realize that there's a chance that that sample leads us to an incorrect decision, if that makes sense. So for example, up here I have in green what I'm going to call a true distribution. It's unknown. And let's just say fictitiously that New Jersey's SAT scores are significantly greater. And that normal curve for New Jersey here is in the green, is what we would expect. And we take a random sample of New Jersey students, there is a chance that we end up getting a score down here. And if that's the case, that we end up getting a score down here, it doesn't look very different than the mean. It's not very different than the mean that we had in the United States. And therefore, we're going to say, you know what? We don't think it's significantly different. We don't have enough data to say that New Jersey's different than the 500. So we're just going to say that, and we're going to have to stick with the idea that our hypothesis is true. All right, null hypothesis is true. Or we can get a sample that ends up giving us a value up in this area. And since this area is greater than where our cutoff was based off of our alpha level, or our level of significance, then we're going to reject what's called reject the null hypothesis. We're going to say that this is so high up here that we believe that New Jersey actually does have a mean SAT score greater than 500. And if that's the case, then we made a correct decision. All right, now I'm gonna finish this now, and the next screencast is going to pick up where we left off right here, and we're going to talk about what a type 1 and type 2 error is, and the whole idea here of having a correct decision versus an incorrect decision. All right, thank you.